Good afternoon, students. This is me back again with you. We are now going to continue with part 2 of chapter 2. Okay, right. Now, where are we? We said that we are going to continue here. Let me just get this color back to blue in case I'm going to be writing here again. Right, so let's see. We speak now about average velocity and speed. Okay, so as a definition, you can see here average velocity is the change in position divided by the change in time. Right, so you have the Vx av for average, and you can see the velocity, but we have x there. That is just a way, it's a notation that is being used. I remember when I was at school, I would have done it like this to show you. V with a line on top of it, and that would also mean average velocity. I don't know if you people use that thing, but different people use different notations. Okay, so here I see from the textbook, using the textbook survey and Jewett, this is what they use for average velocity. The AVE shows its average, right? Okay, and that will be change in position over change in time. Just to go back to that, change in position. What is that? Change in position. Can you see the final position minus initial position? That is also called displacement. And if you remember from school, that is how we would have said that, right? That average velocity would be equal to displacement. Sorry, now I'm writing with my mouse. That's why it goes so slowly and so ugly. Displacement over time. Sorry for this bad handwriting, eh? Okay. Oh, it looks awful. Let's just take it away. Displacement over time. Right. Okay. So that there is your displacement and the change in time. Okay. Right. So that is your definition, the mathematical form here of your definition for average velocity. It must be displacement over time. You just take the displacement from initial to the final position and you divide it by the time. Okay. Right. So they say that Ti and Tf, can you see there we have Xi and Xf, so you have Ti and Tf also. Okay, right. Okay, so on this graph now, figure 2.2, where are we? This graph here, figure 2.2. Okay, let's use that there. I'm first to read what they say there. Okay, so there, the average velocity is represented by the right angle triangle between Pi and Pf. Okay, let's go back there and see. Quickly, let's go back there. Can you see there's Pi and there's Pf, initial point and your final point. So we draw this right angle triangle as you can see here. Right, this one over here, the horizontal one, that will be your delta t, because that's according to your time, and the vertical one will be the delta x. Okay, the change in displacement, change in position, I should say, or your displacement. That's your displacement, or the change in position over the change in time. Okay, right, right, and okay, so that there they show that as an example. You could have go back to the drawing. You could have taken any 2 points. For example, I could have taken point A and point H and draw a line from there to there. Right. And then take that as a right angle triangle Then this here would be your change in time, and this here would be your change in displacement. Right, the vertical one here. Right, so change in displacement over change in time. Any right angle triangle, right? So that will be your average velocity. Look at the shape of the graph. Look at the shape of the graph. But for the average, it will always be of a straight line. Do we see that? The average velocity, it will give you the gradient of a straight line, because this is a formula of gradient. Right? Can you see it? This here? The vertical difference over the horizontal difference, that will give you the gradient of that line. Right? So the gradient of this line will be given by this delta x. Let's call it delta x1 and delta t1. Right? Okay. Right. Okay. Now let's continue quickly. Where are we now? Hey, I jumped the gun here. Okay. So from the mathematical linear graphs, from maths, I should say, we see that the average, it actually represents gradient. I just spoke about that now. Right? The gradient of a straight line between those 2 points. Okay. Right. So that will also be called the average gradient. Right. Between Pi and Pf. And as you can see, it is a straight line between Pi and Pf. Okay, and here, what do they underline here? So this is important then. Average velocity is the average gradient on a position versus time graph, or on a displacement time graph. Right? Okay, so again, average velocity is the average gradient on a position time graph. Let's go back to the graph. The average velocity between Pi and Pf, it will be the average velocity, or the gradient, the average gradient of that line. Between A and H, this average velocity of that line is the average gradient, right? Vertical divided by horizontal distance. As a matter of interest, look at these two gradients. That one is in that direction, and this one goes in that direction. From your mathematics at school, what can you tell me about that? Right, about these two gradients. Right, from that gradient and from this gradient. Can you see it's different? The one is going in that direction, the other one is going in that direction. Right. It is not written in your notes, but I think here it would be worth your while to know here that your velocity in this case here will actually be positive. That's a positive gradient, right? So Vx, right? Your Vx will be positive, and here your Vx average, I should say. Now, I'm just going to put a line up top to make it easy. Right, because to write average will take long for me. Right, there that will be negative, right? So the line in that direction is a gradient, so that's a negative average velocity. And line in that direction is a positive gradient, so that will be a positive average velocity. Okay, that was not mentioned in the notes, so if you can, write it down in your notes as well. Okay, yeah. And here they mention that velocity is also a vector quantity, right? Okay, again, remember, we are going to be talking about this in the next chapter. Okay, that's chapter 3. Okay. While we're busy with that now, if you are going to be speaking about speed, right? Can you see there's a difference now? There we were speaking about velocity, average velocity. Now let's talk about average speed, and that we say will be your distance over time, right? D over delta t, the total distance. See there? The total distance traveled over the change in time over that total distance. Right, and that will be called your average speed. Right, can you see there, there's no x indicated? There's an x indicated to show that is more with respect to position. And here we are just going to speak about v av, so that will actually mean that will be average speed. That is average speed. Right? The notation for average, that is distance over time. And this will always be a positive value because it is a scalar quantity. Speed or average speed is a scalar quantity, whereas velocity or average velocity is a vector quantity. Okay, right. Before we continue, I need to continue with this, but I think I'll take this in the next session. But I see here's an example. They say, let's look at the example. Students, I didn't put examples in here in this chapter as I did in chapter 1. Okay, so I'll just go according to what my colleagues have done. They actually just told us to show the example. Now let's go to this example in the textbook. I think I can just do this, click this here, and there we are, right? I kept this open so that you can actually have a look at example 2.1. This is example 2.1 in the 10th edition. If you people have the 9th edition, just check. I expect it will most probably be the same problem. Yeah. So what do they say? Find the displacement, the average velocity, and the average speed for the car in figure 2.1a. That is between positions A and F. Now where is it? So I suppose we can't look for this now in our notes, right? This is a figure in our notes, but this textbook speaks about figure 2.1a in the textbook. Let's go back to that and see where that is. Oh my, what's happening here now? Oh, I see this thing is closed. Sorry for that, students. I think what I'm going to do is I lost this, so I'll have to do this over again. What I'm going to be doing, if you just bear with me for a bit quickly, and then I'm going to open that for you just now. Right. I just lost that information whilst I was busy with my computer earlier. Okay. So I suppose now you people can see it. We are still, let me just confirm that I am here. Oh, I lost all this thing as well. See what happened here was I know what happened here. Hard drive, the cable just came out, so I must have lost that information. Let me open, but I see I am live with you. Sorry for that, students. Let me just close this as well. I'm not going to say that. Let's just get back to where that is. Where are we now? Now you can actually see what I have already in my folder. Where is the signal? Chapter 2. Okay. So whatever I've written now, that you would have lost now, right? All those drawings that I made, you would have lost. Okay, but it is part of this recording. So that's not major so much. Where are we now? Average velocity. Right, we spoke about this here now, and we spoke about that there, and they said go into this example. So now I'm going to go into the example now, and now I must get to that one. So that if you I don't know if you people have an e-copy, but this it would be worth a while actually getting an e-copy, then actually just have a look at it like this also, or you can get the textbook of the hard copy. So there we are, chapter 2, 1. Can you see it? Motion in one dimension. I'm going to close this and just make this a bit bigger, and then just go through to example. Okay, yeah, I think this is what we were talking about. table 2.1, and there's figure 2.1. Right, so this is something similar to what we have in the notes. Let's just check the notes quickly. It's not exactly the same. That is our drawing. And you can see it goes from A up to H. There, from A to H. Whereas in the textbook we have going from A to F. Right, so these are the values. The first, let's say from A to F, then the time is given here, and the positions, not displacements, eh? These are not displacements. These are all positions on the position axis. Okay. Right, so based on this here, the plot of that is given by this here. Can you see at 0 time, 10, 20, 30, 40, 50. So A is at 30, B is at whatever time that is. You can check, let's just check quickly. 52, C is at 38, and so on and so forth, right? So that was plotted there for you. Okay, right. So what they said there, we must do a few calculations based on this information, or the information we can find in the table. Right. Now, I can't remember what they said in the example, so I might have to just go back. So I hope you don't mind, but I'm going to be running forwards and backwards between these two pages. Here we are. Find the displacement, the average and the average speed of the car. Right. So if you want to find the displacement, remember, it is, you just take the initial position and the final position, so that will be A and F, and you use those two to find the displacement. So if you go back to that, and go what I'd like to show it to you. Right, so there you are. Your initial displacement, the initial position is there, A, and your final position is there. Okay, you can look at it on the graph, but I think it's safer to look at the table. A at 0 seconds, Ti, right? And that will be Xi. That will be 30 meters. And F, can you see, we ignore everything between that. We are only interested in A and F as in the question. So the time there, TF will be 50 seconds, and the position at F will be minus 53. Right, minus 53. Right, so we'll have to go back there. Now remember, we said there was 30 and minus 53. Right. So now you can see here, according to the thing there, you can see the XA is 30 and TA is 0. XF will be minus 53 and TF would be 50 seconds. So if you want to know what your displacement is, it's X final minus X initial, or XF minus X. And that will give you your displacement. And notice here, with respect to your reference position, that is at minus 53. So you're writing there minus 53. And that one is at 30. So you're writing there 30. And that is not minus 38, please. This one is called minus 53, but this one is not minus 30. This one is 30 according to your formula. Can you see that? That minus that you see there is this minus over here. If this had been a minus, 30, then what we would have done, something like this here. We would have said here, let me just get my pen going here. Is my pen not working? There we are. Assuming this thing had been minus 30, then we would have had a minus 53. Don't write this thing down because I'm just showing, assuming. Minus 53 minus, that minus is from the formula. And if this one, we said, if this one had been minus, I would have said minus 30. Can you see? The value, you still consider the value, and that one is part of the formula. Watch out for things like that, eh? Especially if your initial one is a negative value. Let me just take that out, because we don't need that now. I just wanted to speak about the what if type of issue. Anyway, so minus 53 minus 30 is minus 83. So my displacement will then be minus 53. Okay, so remember, between A and F, my displacement is minus 83. So your final position minus your initial position will be your. Okay, good. Right, so what's the next question? Now you must find the average velocity. Right, and now we know, according to what we have learned, the average velocity is, there it is, it's actually given. Average velocity is your displacement over your time. So this the change in position, which we already worked out there, over the change in time. Right, so there, the top section, there we are, minus 83, as you can see there. And at the bottom, it will be your final time, which is 50, minus your initial time, which is 0. All right, okay. So then you can work it out there and write down your answer. As a matter of interest now, students, I'm going to take a bit of a break here now, and we need to just go back to chapter 1. Right, just have a look at this one over here. What did we do? The operation here was subtraction. Right, the operation was subtraction. So remember, in terms of significant figures now, how many decimal places do we have here? Nothing. And there also nothing. So effectively we have 2 positions here, 2 positions. So both of them have 2 positions, but no accuracy indicated. So when we get the final answer, there must be nothing after the comma also, right, for subtraction or addition. Here we also have subtraction and addition, but then we have a division problem, right? We have a division problem. So my final answer must actually be to whatever in whatever, what do you call this thing, significant figures we have. Now let's see if this thing was done properly by our author. All right, your initial position, that is a measurement, right? So that is 30, 2 significant figures, right? Or it could have been 1 also, I suppose, but I'm going to take it as 2. My time is just shown as 0. So that is 1 significant figure, because that's significant. All right, and here my time is, that's 2 significant figures, that's 2 significant figures. So by rights, how do I work this thing out here now? Let's see quickly, right? On top, I get the two digits here according to my subtraction, and that is 1 significant figure. But if I were to subtract here, then the answer for this one will be 50. So that means that's 2 significant figures. So if I divide those two, an answer. Let's see, I'm going to use my calculator and just see what the answer is. There, it's minus 83. I'm just using my calculator and divided by 50. And the answer according to that is actually minus 1.66. That is what the calculator would give, meters per second. Right. For this division, we have 2 significant figures on top and 2 significant figures at the bottom. So my answer must be given to 2 significant figures, which means I must draw a line there, and this must be dropped. This digit must be dropped. Now you can see this digit is more than 5. So that means this one becomes 7. And that's why we have minus 1.7 meters per second. Right, students, please, that is very, very, very important. Whenever we do calculations throughout this book, we need to follow this procedure, considering significant figures. And you can see there that the author did it. The author didn't speak about it, but the author actually implemented the information or the the work about significant figures. Okay, right, please don't forget that. Make that part of how you will be doing calculations. Not only in physics, students, you will see your Elec notes. This topic is also discussed in your Elec notes because it is important there as well. And it's important in all subjects where you are going to be dealing with calculations involving measured quantities. So make yourselves used to this, please. Okay, we've done that. Okay, and notice here, the other thing now, we're getting back to this here, minus 1.7. The negative shows negative, and what would that actually tell you then? If you were to have a graph of these positions, right, a graph of these positions, then that will tell you that your velocity is actually, or your average velocity is a negative gradient, right? That is a negative gradient. Let's go back to our graph quickly and see if that is correct. Between A and F, right? If I have to draw a line between A and F, can you see that? Draw a line, straight line between A and F, and automatically you can see there the gradient. Yeah, can you see that? The gradient of that line. Excuse me. The gradient of that line, you can see there, it's a negative gradient. Right, remember how we indicate positive and negative gradients, right? So we are correct, right? But the average velocity here is then a negative gradient. Okay. Right, please check all these things always, right? Right, make sure that you follow these things and you appreciate it and you understand it, right? Okay, and then the last question is to calculate the average speed of the car. Now remember what we said earlier, the average speed must be distance over time, right? Okay, and here you can see the distance, okay, right? Now let's see if my distance here, my distance is 127. How did we get power 127? I want to go back quickly to my table. Or let's go back here. What is my total distance that I have traveled? Right. Initially, I see here they don't use dots. They actually use these positions of the cars. Right. So this is where our initial point was. Right. I'm going to put a dot there. From there, we move to the right. Okay. We move to the right. A, B, and then we move back to C. You see A to B, and now we move back to C, and there we are going to go in that direction also there, right? Okay, so what this line here on the for this axis, this is your position axis, right? So we started here, we went to that position, then we came back to C, back to D, so that I'm back here at my reference position, then I continue in the opposite direction until we get to F. All right, so effectively from here, we went how much? That way? We actually went, what was that? 52. I'm going to add that, right? From A, went to the right 52 times, right? So I'm going to add that quickly. That will be 52, right? And then what do we add now? Now, let's see. Now, remember, these are all positions, right? These are all positions. Did I say 52? Sorry. Yeah, we started at 30, then we went to 52, but we didn't travel a distance of 52, so I'm actually incorrect. I'm actually wrong. How far did we travel here? We traveled a distance from 30 to 52, that will be 22. So I'm going to change that on my calculator, 22. Right, okay. Right, and then we go from 52, we go to 38. What's the difference between them? It's best to work out the difference between them. 52 minus 38. How much is that there? Oh, I can't do my calculations in my head. Now, what is that? Come, you help me. 14. No? Yeah, it's 14. So now I add another 14 to my 22. Okay. And then from 38, we go down to 0. So a distance of 38. So I plus 38. And then from 0, I go to 37. So I add a 37. And lastly, I go from 37 to 53. Right, from 37 to 53. So how much is that? Let's see, that would be 16. Right, so I will add 16. Right, anyway. Sorry, I made a mistake there. 16, and my answer is 127. Absolutely. I hope you people notice what I did. I didn't just say, I want to say this plus this plus this plus this minus that minus that. Are you with me? Okay. What would we get? Let's see quickly. If I were to say that, I'm just going to see, right? My answer was 127. So I said 30 plus 52 plus 38. And now what about the 0? Right? Minus, there's nothing there. There's a minus 37 and minus 53. And my answer is 30. Can you see? And that is definitely not 30. Definitely not my that I've traveled. How did I find my distance? Let's go through it again. Be careful, eh? From there to there was 22. Right? From there to there was, I came back, right? 14. So I add 14 to 22. Right? Okay, 36. And then I travel another distance from there to 0. So 38 meters. So I add 38. And then from 0 to minus 37, that is a distance of 37. So I add 37. And then from 37 to 53, that is a distance of a displacement of 16. So I add a 16, right, to get my total distance. Okay, right. So as you can see there, according to that, we actually got a distance of 127, and the time again is 50. Right, again is 50. Right, and then we divide those two, and then we can get our answer. And again, you can see here, according to significant figures, I again got an answer to 2 decimal places. 127 divided by 50. What is that? Let me just check quickly. 127 divided. And this is what your calculator will give us, 2.54. Right, 2.54. That is the answer that the calculator would give for this calculation. Right, remember there, I'm sorry, when I added all of them, I get this answer of 127. So that is 3 significant figures, and that will be 2 significant figures. Notice here, please, we don't determine the number of significant figures from just looking at the values that we were using. We first do the additions and the subtractions, and then in this calculation, we look at the significant figures in here. So that one will have 3, this one will have 2, and therefore the answer must have 2 significant figures. The 4 needs to be dropped, and this is less than 5. That's why the answer is 2.5 meters per second. Okay, so that is example 2.1 from the textbook. What I want to do now is I just want to show you here that what I did here, I deliberately changed my notes so that I have a different table and a different graph from that one in the textbook. And obviously, the reason for that is that there you will now have to do the same thing for this one. Okay, as an exercise, you do it. No? For what do we call that there? For the figure in table 2.2, right, between A and H. Okay, I'll do exercise 1. Do the same. For, what did I say? A, H. In figure what did I say? 2.2 of the notes. Sorry for my bad handwriting with the mouse. Okay, not that my handwriting is always good, it's actually always bad. It's an in. And number 2, do the same for, let's say, B, F. Okay, for the same thing there. And number 3, give you another one. Do the same for, what can we give you here? Let's say C, E. Right, in that same table. Okay, so you as an exercise, try to do a similar kind of calculation. Do it for that, right? Remember, sifunda, ukwenza, and ngokwenza. We learn to do by doing. Practice makes perfect. Don't just look at the example. You try to work it out. Now, you saw in that example in the textbook how things were done. So you try to do it for these ones as well. Okay, I don't have this in my notes, so I am going to write a note for myself to remind me that I can actually include that in my notes afterwards as an exercise. Right, at the moment, these things are not shown in the notes that I uploaded to for you, but I'll do this afterwards, and then I'll re-upload these notes. Okay, so let me just write it down. Okay, what I'll do is I'll just end this recording for you, and then we'll continue with the section afterwards. Thank you.